Good evening, everyone. Welcome to O-level physics lesson. Today we'll be doing the theory of the chapter 8, thermal processes. Okay, my name is Mr. Chu. Okay, today is the Monday, 28th of August. Okay, there are three topics under thermal physics. Okay, so we have finished the first topic, which is the kinetic model of matter. Okay, so this will be the second topic, which is the thermal processes. And then we will talk about the last topic next time. The last topic of thermal physics is thermal properties of material. Yeah. So basically, it's like I've covered a little bit of that in the last topic, which is about internal energy. Okay, what happens when you change of state and so on. Okay, and how much energy there is needed to increase the temperature of an object, as well as to change the state of an object. Okay, so that is for chapter 9. Okay, so there are only 3 topics for your new syllabus. Previously there's 4 topic or 5 topic. They removed the topic on the temperature thermometer. Okay, so that is something that they really take away lah. Previously they actually put it under other topics. Okay, so let's begin. Hello, Zachary. Okay, if we can take a look here. Okay, what I mentioned just now is that we are now at thermal physics. Okay, we are at thermal physics. Okay, we have gone through chapter 7, kinetic particle model of matter. Okay, most of you tell me that you know the chapter quite well. It's just a matter of practice. Okay, today we'll talk about thermal processes. And then in the future, after we have a new president, we will talk about thermal properties of matter. Okay, so let's talk about thermal. Okay, so thermal physics is about heat. Okay, it's about heat. Okay, so we will be talking a bit of this one. Okay, energy exchange will take places between bodies of different temperatures until thermal equilibrium is reached. Okay, so that is what we're going to cover today. Hold on. Okay, we're going to cover this one. Okay, so energy exchanges will take place between bodies of different temperature. So the key thing is that there must be a difference in temperature for thermal energy or energy in a thermal store, okay, for heat to move. Okay, until when the two bodies have the same temperature, there will still be an exchange in energy, but the exchange will be net zero. Okay, the exchange will be net zero, and we call that thermal equilibrium. Okay, equilibrium. Okay, then for this topic today in chapter 8, okay, we'll also be talking about energy transfer. Okay, we'll go through 3 processes, okay, called conduction, convection, and radiation. Okay, so just to check with you all, have you all learned these 3 processes in lower sec? If you have learned these 3 processes, give me a yes reaction. If you have not learned these 3 processes, give me a no reaction. Okay, Zachary, are you there? Okay, so in O-level physics, we'll be talking about it slightly more in detail. I don't think that is much more complicated compared to lower secondary science. Okay, so this topic should be quite easy for all of you. Okay, so what is this topic about? Okay, so we're going to talk about 4 parts. Okay, the first part is about thermal equilibrium. Okay, I will explain what is this thermal equilibrium to you. Okay, then we'll talk about the three processes of the energy, thermal. Okay, then we're going to talk about the three processes of energy transfer. Okay, energy transfer, thermal energy transfer via three ways: conduction, convection, radiation. So let me start off with thermal equilibrium. Okay, do you know what is thermal equilibrium? Okay, so thermal equilibrium means that energy is only transferred from a region of higher temperature to a region of lower temperature. Okay, so if there's no difference in temperature, there will be no heating taking place. Okay, there will be no energy transfer taking place. Okay, so if there is a change, there's a difference in temperature, the thermal energy will only be transferred from a higher temperature to a lower temperature until we reach a state of thermal equilibrium. Okay, that is when the two region has the same temperature and there is a net, okay, there is actually no net transfer of energy between them. Okay, so I'm going to write down the definition of thermal equilibrium, and I want all of you to actually write it down for me as well. Okay, so thermal equilibrium describes, so I want you all start typing, a state in which two or more objects have the same temperature and that there is no net transfer of energy between them. So there may be still transfer of energy between them, but from A to B and B to A is still the same. Okay, so there's no net transfer. Okay, that doesn't mean that there's no transfer. No net transfer doesn't mean no transfer. It just means that A to B, energy from A to B is equal to the energy from B to A. Okay, so if you are okay, type it out for me. Write down thermal equilibrium describes blah, blah, blah. Okay, once you have typed it out, we'll move on to the next one. Yeah, you're still typing. Okay, so you all go and type it out for me. Thermal equilibrium describes what? Okay, Yishuan, thank you. Now the rest of you, please type out what is thermal equilibrium. Okay, hurry leh. Okay, thank you, Zachary. Thank you, Ray Hong. Thank you, Sishan. Okay, so this is the definition that you all need to know for the first part. We will not go through much about thermal equilibrium anymore for today's lesson. Basically, when we put two items of different temperature together in a natural setting, okay, the energy will actually flow from a region of higher temperature to a region of lower temperature. Is that clear? Okay, that is when there is a natural setting. So for example, your room, okay, is very hot. How does the air conditioner cool your room down? By right, region of region of high temperature will transfer energy to a region of lower temperature. Am I right to say that? Okay, but in an example of an air conditioned room, or in your refrigerator, or in a freezer, that seems to be opposite. Okay, what's happening here? Okay, so when we talk about this energy transfer from a region of higher temperature to a region of lower temperature, this happens in a natural setting when we don't force anything to it. Okay, just like for example, if I were to heat a glass of water, okay, the water by right shouldn't be becoming more hot, right? Okay, because the surrounding is cooler. Okay, but you are inputting energy to it to make it hotter. Okay, so just like our air conditioner and freezer and fridge, why are things able to cool down? Okay, because there is an external influence. Okay, that cause the energy to be transferred from a lower region, colder region, to a hotter region. Okay, because of an external influence. Okay, so if there is no external influence, what will happen in the natural world, in this natural universe, is that energy will always be transferred from a region of higher temperature to a region of lower temperature. Are you clear about this? Okay, if you understand what I'm saying, okay, give me a yes reaction. Okay, Zachary, are you okay? Okay, so we have discussed that energy hold on. Okay, we have discussed that energy will transfer from a region of higher temperature to a region of lower temperature. Okay, we are now convinced about this. Okay, if you're not convinced, just assume that this is the law. Okay, the next thing that we are going to talk about would be how does this transfer takes place. There are three vehicles of transfer. Okay, this energy can be transferred via three different ways. Okay, or three different vehicles. Okay, don't use the word vehicle. I'm just using vehicle to let you all try to imagine. You're actually a truck carrying the thermal energy from a hotter region to a colder region. Okay, so you got three different vehicles that do that. Okay, so the three ways are conduction, okay, convection, and radiation. Are you clear about this? Okay, so let me repeat the main point that you need to know in this topic. First of all, energy can only be transferred from a region of higher temperature to a region of lower temperature. Okay, this how does it take place? There are three ways. Okay, by conduction, by convection, and by radiation. Okay, so let me explain to you the proper definition of conduction. Okay, conduction is a process of energy transfer where energy is transferred through the passing on of vibrational motion from one particle to another. Okay, so I want you to prepare this statement. Later you need to type it out. Okay, conduction is a process of energy transfer. Okay, all these three are processes of energy transfer. Okay, but what is unique about conduction is that conduction is energy is only transferred via the passing on of vibrational motion from one particle to another. Okay, so let me share with you some keyword. You need particle for conduction to take place. Okay, particle means substance. Okay, it means matter. Okay, you know the matter that we learned, M-A-T-T-E-R, not the M-E-T-A-L. Okay, so you need substance, you need a matter, okay, for it to occur. Okay, so just imagine you have two particles. Okay, let me draw out for you. Just imagine, you got two particles, okay? They are both vibrating. Okay, so from the act of the vibration, they will touch each other, right? So when they actually touch each other, okay, the particles hold on to some thermal energy. Okay, they have some thermal energy, E. So as they vibrate, it passes the thermal energy to the next particle. Okay, via the vibration of vibration contact of each particle. Are you clear about this? Okay, so when the particles are vibrating and they just like for example, all of you are standing in one straight line. Okay, and I pass you a beanbag. You just pass the beanbag from one person to the other. Okay, that is how conduction takes place. Okay, it's where the energy is transferred through the passing on of vibrational motion from one particle to the other. Okay, so conduction will only take place when there is a particle. Okay, meaning that it will not take place where there is no particle. Are you clear about this? Okay, it will not take place where there is no particle. Meaning, in a vacuum. Okay, in a vacuum. For example, this is a sun. Okay, maybe 10 million degrees Celsius. This is the earth. Okay, maybe it is only 10 degrees Celsius. There is a difference in temperature. This is higher temperature. This is lower temperature. By right, energy is supposed to transfer from a region of higher temperature to a region of lower temperature. Okay, but it will not be transferred by the method of conduction because in between is vacuum. There is no particles. Okay, so the energy, the thermal energy from the sun will not be transferred via conduction to the earth. Are you clear about this? Okay, that will not happen. Okay, the conduction by the sun will not be transferred to the earth via conduction because there is no particles in between. Conduction cannot take place. Are you all with me? Sishan, are you there? Okay, on your camera. Okay, so for conduction to take place, you need to have particles between the two regions. Okay, number two. Okay, we have also learned in primary school. There are some items that are good conductor of heat. There are also items that are poor conductors of heat. Okay, so you learned this in primary school. And we learned that in primary school, basically, good conductors of heat are mainly metals. And then the poor conductors of heat are mainly non-metals. Okay, so what makes metal special? Okay, what makes metal special? Okay, so basically, conduction, this process called conduction is a very slow process. Just imagine why. Because you are actually transfer the energy from one particle to the other. So conduction inherently is a very slow process. Okay, because you're just passing the energy from one particle to the other, It'll take some time to do that. Okay, but however, why is metal a good conductor of heat? Okay, can you see the word? In primary school, you do not know why you use the word conductor. Okay, but now you understand why. Okay, when we talk about conductor, it means that heat is transferred by conduction. Okay, so metals are good conductors of heat, whereas non-metals are poor conductors of heat. Okay, why is that so? Okay, let me just draw again. A normal material. Okay, let's say we talk about solid. Okay, the particles we learned in the previous topic. For solid, the particles are arranged in a fixed pattern. Okay, so what they do is they just vibrate. Okay, they just vibrate. Okay, so when here is hotter and here is colder, the one on the left will vibrate more because when it's hotter, it has a higher temperature. When it has a higher temperature, it has a higher kinetic energy. So it will be vibrating faster. Okay, colder also vibrating lah, but vibrating slower. Okay, so there is more kinetic energy on the hotter side. So when it vibrate, when you hit the next one, you'll cause the next one to vibrate a bit more, whereas the original one will start to vibrate a bit less. So the energy is transferred from a higher vibration to a lower vibration, and you will transfer from particle to particle until all of the particles have the same kinetic energy, meaning that all the particles has the same temperature. Okay, but energy will still be transferring left to right, but the net energy transfer is 0. Okay, so 5 energy can still be moving from left to right, but on the right, also 5 energy moving from right to left. Okay, there's no net transfer energy between them. They are still transferring energy, but it is 0 net transfer. Is that clear? Okay, so that is how conduction takes place. That is one of the way, the easiest way, okay, but also one of the slowest way, okay, for heat to transfer energy. Okay, for an object to transfer energy from a region of a higher temperature to a colder temperature. Okay, so this solid can be wood. Okay, it can be wood, it can be metal, aluminum, steel. Okay, it can be any solid material. Okay, energy will be conducted, will be passed from one particle to the other particle by the vibrational motion. Clear? Okay, so the next thing I'm going to share with you is what makes metal a good conductor of heat. Everything being equal, they should be quite slow lah. But metal conduct heat much faster than non-metal. Okay, why? Okay, the only reason why is that besides the vibrational motion from one particles to the other particle, metals itself also have this thing called free electron. Okay, they have free electron moving throughout the metal. Okay, we call this free electron. Okay, so these free electrons make the metal a good conductor of heat as well as a good conductor of electricity. Okay, what's happening here? Okay, electrons in matter are not fixed to the atom. I repeat myself again. Electrons in a matter, we call this a valence electrons. Okay, the outer shell electrons, the valence electrons are not fixed to the atom. Okay, so these small electrons are able to move freely and easily between the particles at very high speed. Clear so far? So, as the particles cannot move, can only vibrate, whereas a free electron can move easily amongst the matter. Okay, so this free electron can also carry the thermal energy from a region of a higher temperature all the way to the region of a lower temperature. Okay, so this free electron itself, okay, collectively will be moving, okay, when they actually collide with the next, either the nucleus or the next electron, it will actually collide slower, causing the particle to move a bit faster. So that causes that particle to have a greater temperature. Is that clear? Okay, so my point is this. Conduction, okay, is a process of energy transfer where energy is transferred through the passing on of vibrational motion from one particle to the other. So there are two ways about it. In all material, solid or liquid, or even gas, okay, when they touch each other, when they actually vibrate and actually collide with each other, energy is transferred from one particle to the other. So the one that's moving faster, when it collide with the one that's moving slower, energy is transferred. The faster particle will become slower, temperature drop. The slower particle will become faster, the temperature increase. Okay, so there's two ways of doing it. Via particle vibration, number one. Okay, or we call it the collision of particles in a fixed position. In solid, they're in fixed position. In liquid, if they are not moving, conduction can also take place. Is that clear? Okay, conduction takes place when there's particle. So it actually can take place in solid, liquid, or gas. Okay, but for now, we talk about solid because it is the easiest way to explain conduction. Then, besides the collision of particles, or vibrating particles, a second way of transferring energy is via the collision of the free electrons. Okay, they are able to move easily and quickly within the material. Okay, and the presence of these free electrons makes matter a good conductor of heat because it allows energy to be transferred much faster compared with a material with no free electrons. Okay, up to here, are you all clear? Okay, if you understand the meaning of conduction, can you give me a yes reaction? Okay, so I have covered mainly conduction in solid. Okay, conduction can also occur in liquid and gas. Okay, conduction can also occur in liquid and gas. Same thing is by the collision of a vibrating particle. However, the particles in liquid and especially gas are much further apart. Okay, liquid is only slightly apart, but in gas is much further apart. So this actually make gases a very poor conductor of heat. Okay, is that clear? Okay, it actually makes air a poor conductor of heat. So a lot of times where you want to prevent or minimize air heat transfer, we try to include air within the solution. Okay, because air is a poor conductor of heat. Okay, or you can say that air is a good insulator. Okay, so conduction will still occur in liquid and gas. Don't just think that conduction only occurs in solid. Conduction can also still occur in liquid and gas. I'll give an example of a conduction happening in a liquid. Okay, let me explain this. Let me erase this. Okay, when will conduction occur in a liquid? Okay, we are very used to heating water. Okay, we are very used to heating water from the bottom. Correct. Okay, we're going to learn this next. Convection. We actually learn we heat water from the bottom. When we heat the water from the bottom, convection current occur. Okay, we're going to talk about that later. So it makes the heating process faster. Now, let's assuming I put the heating element at the top of the liquid. Okay, at the top of liquid. When you heat the liquid at the top, the temperature goes up. Am I right? But does it produce a convection current? Okay, when a liquid gets heated up, it expands, right? Because you become there's a more heat, you expand. When it expands, it becomes less dense. So it will still remain on top. There'll be no movement, okay, of the liquid. There'll be not much movement of the liquid within the liquid. Okay, but over a long time, the liquid at the bottom will still be heated up. Okay, so in this kind of process, where there is no convection current, where the liquid doesn't move inside, okay, because once you heat up the liquid, it will become less dense, it will remain on top. The only way for the energy to be transferred down is via conduction. Okay, are you clear about what I'm trying to say now? Okay, so if I were to put a heater in a room, at the top of your room, or if I put a heater at the top of your liquid container, okay, that contains a liquid, the liquid will eventually get heated up eventually, but it will take a long time. But why does it get heated up? Okay, it's through the process of conduction. Okay, so what I'm trying to say here is that conduction will also take place in a liquid or a gas. Okay, in this case, if I put a heating element on top, for the energy to move down is mainly via conduction. Are you all with me? For the energy to be transferred from a hot region on top to the cold region on below is mainly by conduction. Are you clear about this? Okay, maybe when I talk about convection, you all will start to understand what I'm trying to say. Okay, so up to now, if you are very clear about conduction, give me a clap reaction. Okay, so we are halfway to this topic. We have talked about thermal equilibrium. We have talked about conduction. Okay, I'm mainly talking about the concept. If you understand the concept, there's no need to actually remember any more things in this topic. The next thing is just practicing the question. Okay, if you understand the concept, it's actually very simple. Okay, so next, we're going to talk about convection. Okay, what is convection? Convection is a process of energy transfer. These three are all energy transfer process by means of convection currents of a fluid. Okay, the fluid can be a liquid or gas. Okay, in primary school we use air. Okay, but in O-level physics we don't use air. We don't even use gas. We don't even use liquid. We use the term fluid. Okay, fluid encompasses both liquid or gas. Okay, due to a difference in density. Okay, so this is the definition of convection. Convection occurs, okay, because there is a convection currents of a fluid due to a difference in density. Okay, let me go through in detail. I'll use the same example. I'll use two examples, okay. Anything about heating. You want to heat something, you want to heat a bowl of water. We always heat it from the bottom. Okay, we don't heat it from the top. Okay, we always heat it from the bottom. Why? Okay, let's discover point number one. And point number one, when you heat the water, okay, when the temperature increases, what happens? It will expand. Okay, expand means volume go up. Correct. When the temperature increases, the volume increases, but the mass remains the same. The number of particles, the number of matter remains the same. Clear so far? Okay, so mass over volume. This one remains the same and the volume goes up. What happened to the density? Density will go down. Is that clear? When your mass remains the same, but your volume increases, means the same number of mass taking more space. They are more spread out, correct? When they are more spread out, they are less dense, the density drop. So when the density drop, it will go up. Is that clear? Okay, so the hotter, in this case, in primary school, we say hot air rises. You remember that? Okay, so now in O-level physics, we don't say hot air rises, we don't say hot water rises, we say hot fluid rises. Okay, why? Because when the volume increases, density drop. So the hot fluid will rise. Okay, the hot fluid will actually rise. Okay, so number two, the hot fluid rise. Then number three, what happened? Because the hot fluid rises, it will take the place of there's actually some gap between, right? So what happens is the surrounding denser, cooler fluid, okay, the surrounding denser fluid will sink and take the place of the rising hot fluid. Is that clear? So when the particles go up, come down, go up, come down, we actually form a current. Okay, you can, if you actually were to put some dye in the water, as you heat up the water, you will see that the dye moving. inside the water. Okay, we call this the conventional current. Is that clear? Okay, we will see a conventional current when you heat up a water. Okay, so let me repeat the 3 points again. Number one, when you heat up the water at the bottom, the temperature goes up, it expands, the volumes goes up, then the density will drop. Okay, the density will drop. Clear so far? Okay, so when the density drop, the hotter fluid, in this case the water, will rise to the top. As it rises to the top, there is a space left behind, right? So the surrounding denser fluid will actually take the place, you will actually sink and take the place of the rising fluid. So this process repeat again and again, you form a convection current, and that is how the energy is actually transferred throughout the fluid. Okay, how is it different from conduction? Conduction, the particles just vibrate. So it is just transferring of energy from one vibrating particle to the next vibrating particle. So it's a very slow process. Whereas for convection, as the hotter, the warmer, less dense fluid move, okay, it actually rises. As it rises, okay, is helping to spread the energy throughout the liquid. Are you clear about this? Okay, so because the particles actually move in a convection, therefore the process of energy transfer is faster for convection compared to conduction. Are you clear about this? Okay, convection is a faster process compared to conduction because in convection, the particles actually move, okay, and form a convection current. So when there's a current, it actually spread the energy faster. Is that clear so far? So as it moves upwards, okay, it's also spreading the energy by conduction. Okay, so with the movement of the particle, in addition to conduction, the energy transfer process is now much faster. Are you clear about this? Okay, if you are clear about this, give me a yes reaction. Zachary and Sishan, are you okay? Zachary, are you there? Okay, I'm going to use another example. Where should we place our air conditioner? Okay, nowadays, if you look at your school, you look at your home, your air conditioner are placed on top. Okay, why? I'll explain in a while. But if you are staying in an older estate, let's say your parents' room, you will see that the air conditioner is at the bottom part of the room. Okay, that is not the right place to put. Okay, so same thing. When we have a glass of water and we want to cool the water, okay, the ice will be on top. So what happened first? Number one, okay, when the temperature is low, the liquid there will contract. So the volume goes down. When the volume goes down, the density increases. Okay, so what happened is the colder liquid will sink. Okay, number two, the colder, more dense fluid will sink. Then number 3. What happens next will be number 3. The hotter, less dense fluid will rise and take the place of the sinking fluid. Sinking colder fluid. Is that clear? Okay, so when you put your air conditioner at the top of the room, you cool the air around it. When you cool the air around it, the volume will go down, density will go up, the cool air will sink. When the cool air sinks, the hotter, less dense air will rise and take over the place of the cooler air. Okay, so this process repeats and you'll form a convection current. Okay, and this will actually helps the air in the room to cool down faster. Is that clear? But if you were to put the air conditioner at the bottom, okay, we put air conditioner at the bottom, the temperature goes down, volumes goes down, density goes up. The cold air will remain at the bottom, and the only way for the whole room to cool is via conduction. Okay, where the hotter air will conduct energy to the cooler air, and slowly, very, very slowly, then the whole room will cool. Is that clear? Okay, next thing I want you to know is that for these two processes, okay, it will require, okay, a metal for it to, it require metal, okay, it require, okay, no, the metal is not a word. It require a medium, a physical medium for the energy to transfer. Okay, so for conduction and convection to take place, it will require a physical medium, okay, for the energy transfer to take place. Okay. Then for radiation, it does not require a physical medium. Okay, it does not require a physical medium, meaning that energy is able to transfer via vacuum. Okay, for radiation, you don't need a medium to take place. It can actually transfer, okay, through vacuum. Okay, so for electromagnetic radiation, it does not require a material medium, and how fast it actually transfer depend on three factors. Okay, so let me erase this one. Okay, you are very clear about how convection takes place, right? How to explain also, right? If you are very clear, let me just erase all these first. And let me give you the definition of radiation. Okay, so radiation is the process of energy transfer by electromagnetic waves. Okay, it does not require a medium. Okay, so radiation is a process of energy transfer by an electromagnetic wave. Okay, it does not require a medium. Okay, so just now we talked about the sun. How the sun transfer heat energy to the earth. Okay, how the sun transfer heat energy to the earth, okay, is by electromagnetic radiation. Okay, is that clear? Okay, how it can actually travel through vacuum at the speed of light. Okay, so the speed is 3 times 10 to the power 8 meter per second. So from the sun to the earth, this will take about 8 minutes. Okay, how far is the moon to the earth is about 1 second. Okay, the sun is much, much further away. It will take about 8 minutes, okay, for the speed of, for the light to travel to the earth. Same thing, the heat of the sun will actually takes about 8 minutes to reach the earth. So the heat that you feel on your skin when you stand out in the sun is the heat by the sun 8 minutes ago. Is that clear? So when the sun now suddenly has no more light burn out, no light and no more heat, we'll only know it 8 minutes later. Is that clear? So what we see in the sky, the stars, the sun, okay, the stars, they are all, what we are looking at is not the present, but we are looking into the past. Okay, so let me repeat myself again. When we look at the moon, we are looking at the moon 1 second ago. When we look at the sun, we are looking at that sun 8 minutes ago. Okay, when we look at the nearest star to our sun, okay, the nearest star to our sun, it is about 3 years ago. We look at the star, you can see the star that is nearest to our sun. What the light that we see is the light that is produced by that star 3 years ago. Is that clear? So the many other stars that we see in the sky are many, many years ago. Okay, so the heat from the sun travel to the earth via electromagnetic radiation, and it travel at the speed of light, which is 3 times 10 to the power 8 meter per second. Are you all clear? Up to now, any question for me? Okay, so which electromagnetic radiation are we talking about? Specifically, we are talking about infrared. Okay, infrared is the radiation that most of the heat sorry. Infrared is one of the radiation that is being transmitted by the sun to the earth. Okay, the other form of radiation will be visible light. Okay, visible light, radio wave, and so on. So all these radiation will be actually transferred from the hotter region to a cooler region at the speed of light without a medium. Is that clear? With a medium, it'll be slower. But without a medium, you'll be traveling at the speed of light. Okay, so what are the factors? Okay, before we talk about it, now we talk about Earth first, or any object that we know. Any object that has a temperature above absolute zero. Okay, any body with a temperature above 0 Kelvin, okay, will be able to do two things. Okay, you'll be able to absorb radiation. You'll be also be able to emit radiation. Is that clear? Absorb means take in. Emit means give out. So any body or any material that is vibrating, that has a temperature above 0 Kelvin, will be able to absorb radiation or emit radiation. So how fast this absorption or emission takes place, okay, depends on three main factors. Okay, it depends on the surface color and texture, surface temperature, as well as surface area. Is that clear? So let me talk about the surface color and texture first. Okay, so color wise, wait, there's no space here. Okay, but can you all remember these three things? Let me just clear the whole thing. Okay, so when you go out, do you all remember color wise? People tell you, if you don't want to feel hot, should you wear white or black shirt color? Can you write it down in the chat? Should be wearing white or black? Okay, so we talk about color first. White versus black. Okay, white is a good reflector. Okay, then we also talk about absorber and emitter. Usually, if you are good at absorbing, you're also good at emitting. Okay, and then if you are good at reflecting, you're bad at absorbing. So a white material, a white shirt that you wear is very good at reflecting heat away. Okay, so white is a good thing to actually feel cooler because it is a bad absorber and a bad emitter. Are you clear about this? But let me ask you a question. Most of your parents, if you have a car, what color is your parents' car? Can you tell me? If your parents have a car, what color is their car? Or all of you have no color, no car? Yishen says that the parents' car is black. Then the rest of you? No car at all. So Yishen, if you tell your parents, if you want to have a cooler journey, okay, you should go and spray the car white. All right. Okay, so because white reflect heat away better, okay, and yet is a poor absorber of heat. Okay, then black will be the opposite. Black is a bad reflector, but it absorbs heat very well. It also emit heat very well. Clear so far? Okay, likewise, we talk about shiny, okay, versus matte. Same thing, shiny is a surface that is a good reflector of heat, but it's a poor absorber and a poor emitter of heat. The opposite of shiny is matte. Matte is a poor reflector of heat, but a good absorber and a good emitter of heat. Is that clear? Okay, lastly, we can also talk about smooth and rough. But can you actually imagine? Smooth surface are also a very good reflector, just like our mirror. Our mirror is so smooth, it reflects light, correct or not? Okay, so a smooth surface, you'll be able to reflect heat as well. Okay, so a smooth surface would be a bad absorber as well as a bad emitter. Whereas a rough surface will be a good absorber and a good emitter. Okay, so surface color and texture. What are the good radiator? A good radiator will be a matte, rough, and dark color. Okay, so a body that has a matte, rough, and dark color surface, okay, will be a good emitter. Is that clear? Are you all with me? Okay, the next thing, surface temperature. Okay, the surface temperature. Okay, a higher surface temperature, the higher the rate of emission of radiation. I repeat myself again. If the temperature of a material is higher, it is actually a better emitter of radiation. Clear so far? Okay, lastly, surface area, very simple. You have me a guess. A bigger surface area will be a bigger emitter or a poorer emitter. Can you tell me? Surface area, which one will give a better emitter? A body with a bigger surface area or a smaller surface area? Which one actually makes sense to you? Hello, are you there? Okay, a bigger surface area will also be a, okay, these are all better emitters. Okay, or we call that better radiators. Okay, so a surface that have all these characteristics, matte, rough, dark colored, higher temperature, bigger area, they are all better radiators. Are you clear about this? Okay, so are you clear about the three vehicles of energy transfer? If you understand, give me a thumbs up reaction. Only Yishan understand. The rest there? Sishan also, thank you. Rui Ho and Zachary, do you understand? Okay. Now the last part of today's lesson will be on we are going to apply these three things, conduction, convection, radiation to everyday example. So I'm going to show your notes, which I'm going to give it to you all via your parents. And that will be the last part of today's lesson. Hold on. Okay. So let me just go through this very quickly. Then we go through some example and that'll be the end of today. Okay, so I mentioned before, thermal energy will be moving from a region of higher temperature to a region of lower temperature. Okay, there will only be a net flow of thermal energy when there's a different temperature. Okay, it only move from a region of higher to a region of lower. So for objects in the thermal equilibrium, they will have the same temperature. There'll be a zero net transfer of thermal energy. Okay, I mentioned these 2-3 times today. Are you clear about this? Okay, the next thing, conduction will need to go through a medium without the medium moving. Clear so far? Okay, so the notes I'll give it to you. Okay, so I'm just summarizing. Conduction is the transfer of thermal energy through a medium where the medium is not moving. Whereas convection is a transfer of thermal energy via convection current in a fluid due to a difference in density. So if I use this definition to explain, it will be through a medium via a flow of the medium, okay, due to a difference in density. Clear so far? And metal makes a good conductor because it has a free, fast-moving electrons. Understand so far? Whereas liquid and gases are poor conductor of heat, okay, because they are spaced further apart, making the collision less frequent, so the transfer will be slower. Clear? So convection, just quickly read through these 2 points. I mentioned this just now. You should understand quite easily. Okay. Then for radiation, is a transfer via electromagnetic wave without any medium. Okay, this is the only process that can transfer heat without a medium. And what are the 3 factors that affect the rate of transfer? The higher the temperature, the higher the rate of transfer. The larger the surface area, the higher the rate of transfer. Black, dull, and rough surface, okay, will absorb and emit infrared radiation better than the bright, silver, smooth, and shiny surface. Okay, so processes. I'll only go through one example. Okay, in a lot of physics textbook, they use the thermal flask or vacuum flask as an example because it makes use of these 3 theory to minimize heat transfer. Clear so far? So first of all, we talk about vacuum. Okay, in the thermal flask or vacuum flask, you see this white color part here is made up of vacuum. So when most of the surrounding of this liquid is surrounded by vacuum, conduction and convection will not take place. Okay? So the heat will not be transferred out of the material via conduction or convection. The only place that will do that would be via the stopper here. And this stopper, you purposely use a plastic. Why? Because plastic is a poor conductor of heat. So the rate of conduction through the stopper will be reduced. And because it's a cap, air will not go in and go out easily. Air inside will not evaporate easily. So the liquid inside will not gain or lose heat via convection. Are you clear so far? Then, what is holding the vacuum? Okay, you'll see a lot of this cork. Okay, this cork itself supporting the outside of the vacuum. Okay, why? Cork contains a lot of air pocket. And cork and the air pockets are all very poor conductor of heat. Okay, so having an exterior material made of cork, it actually minimize heat transfer by conduction. Clear so far? Okay, just now we talk about vacuum. When you use a vacuum inside the flask, okay, in this flask, it will prevent heat loss by conduction and convection. And lastly, on the inside surface of this vacuum, okay, we will use silver surface. Why? Because black, dull, and smooth surface, black, dull, and rough surfaces are good radiator. Whereas on the other hand, we use a very bright, okay, glass is like very bright, very smooth surface that is covered with silver to make it even smoother, so that any heat that is able to escape via radiation will be reflected back into the flask. Okay, or any heat from outside will actually reflected back in out to the surrounding. Okay, so heat transfer via radiation will be minimized. So a vacuum flask make use of the theory that we learned about conduction, convection, and radiation, and that allows your hot or cold liquid inside the vacuum flask to remain hot or cold for a much longer of time. Is that clear? Okay, if you understand about all what I mentioned so far, give me a yes reaction. Okay, so vacuum flasks talk about all the conduction, convection, and radiation. Okay, so let me talk about a bit more examples of all this happening. So conduction, what example do we have? Okay, we use hair dryer. Hair dryer is an example of using conduction to actually dry our hair. Okay, instant water heater is also using conduction. Okay, thermal wear, where you have a lot of air pockets, okay, inside your clothes. Also make use of conduction to make you stay warm. Okay, so if you go to other country, you realize that their window is double or even triple glazed window. Okay, why? Okay, so your window itself is made out of two windows. There is an air pocket in between. Air is a very poor conductor of heat. Okay, so therefore, when you go to overseas, you see a window is made out of two or even three layers. Okay, because they want to have the air layer in between to minimize heat loss or heat gain in the building. Is that clear? Okay, so this is some example of conduction. Okay, convection. Okay, many I mentioned just now a lot electric kettle. Okay, where all your kettle make use of convection to heat your water. Okay, hot air balloon. You heat up your balloon, make it less dense so that it will rise. Okay, so hot air balloon make use of convection to help you rise. Okay, this one you learn in lower sec or in primary school. Okay, your sea breeze and your land breeze. How many of you need me to explain these two breezes? Okay, if you need me to explain the two breezes, give me a yes reaction. If you don't need me to explain, then tell me, give me a no reaction. Okay, Yushen, what do you want me to explain? Okay, so there is land and there is sea. Okay, and we know that land is solid, sea is liquid. Okay, so because it's solid, it will heat or cool faster. Is that clear? So daytime, it will heat up faster. Daytime, it will heat up faster. So the air above land will rise. Is that clear? The air above the land will rise because the land is hotter than the sea. So the sea, the air actually, during daytime, we talk about day. The sea itself, okay, the land, the sea itself, because it's cooler and more dense, and because there is air, and the air actually rises, Okay, you will actually get sea breeze. Okay, so sea breeze happen during the day. Okay, because land heat up faster compared to the sea, the air above the land will actually rises. Okay, because volume increase, then density decrease, so the air will rise. When air rises, there's a gap here, right? So air from the sea, which is cooler, will come in. So daytime, you go walk by the beach, you feel the air, you feel the breeze coming in from the sea. Okay, you will feel actually cooler. Okay, then night time, what happened? Night time, Okay, night time, what happened? Let me write down. Okay, so night, it will cool faster. The land will cool faster. Okay, so the air, so the sea will become hotter, right? So the air will actually rise up from the sea. Okay, so you actually cause a land breeze. We call this a land breeze because a breeze come from the land. Okay, so land breeze occur during the night. Because the land will cool faster, the sea remains hotter, so the air above the sea will actually rise. The air from the land will actually fill up the place. So we call this the land breeze. Is that clear? Can? Okay, so example of radiation. Some practical example is greenhouses. Okay, we allow radiation to actually from the sun to enter the greenhouse. Okay, another example will be space blanket. Okay, space blanket is a blanket that is very shiny and smooth. So for example, if you are in a very cold water, okay, we'll use the space blanket to cover you to protect you, okay, from the radiation. Okay, so these are examples that we have gone through. And one of the example that we talked about just now is vacuum flask. Okay, vacuum flask make use of all three of these example. Okay, of all three of these theory to actually make a vacuum flask. Okay, okay, now I have finished the topic on this topic. Okay, it's just a little bit more in depth compared to your lower secondary topic on this. Okay, so my essay question to you all is number one. What are the three thermal transfer processes? Okay, how well, okay, how much you learn today on this topic? How well Mr. Chu teach today on this topic? Okay, once you give me your essay question, essay answers, I call your name, you may leave. Hey, Wei Ho, you may go. Yu Xuan, you may go. Zachary, you may go. Zixuan? Hey, Yishan, you got any question for me? Hey, Zixuan, question 2 and 3, what's your answer? Okay, Zixuan, you may go. Yishan, any question for me?
No.
Okay, because you're still around. Okay, now you can go. Thank you for
Oh,
being. Good
okay.
night and goodbye. See ya.
Bye.
Bye.